All right. Hello, everyone. Welcome to Skype a Scientist Live. This month, we're going to be talking about physics and how physics affects us every single day with physicist and science communicator, Madelyn Leembruggen. So thanks for joining us, Madelyn.
Yeah, I'm so excited to be here. I've heard a lot over the years about Skype with scientists, so excited
Awesome.
to be on this side of things.
Amazing. Glad you're here. So here's how this is going to go. We're going to have a brief introduction, and then you are going to ask as many questions as we can fit in the next 45 minutes. If you have questions, please submit them to the Q&A in the bottom. It helps me keep track of all the questions. Please only submit questions one time. Generally, there's more questions than we have time for, so only submit them once to help me out. And also, if you find that your group is super curious and has more physics questions than we have time to get through in this 45-minute session, you can always request a physicist for just your classroom for free at skypeascientist.com. That's enough of me, though. I'm going to hand it over to our physicist, Madelyn.
Yes, I will share a couple slides that I made for us to think about this. Hold on, sorry, I think my view is wrong. Let me switch this real quick. I should have,
It looked good to me. It looked like a
okay,
regular slide.
that's good. Let's see. Okay, let's try it this way. Um, does that look okay?
Looks good.
Okay. Yes, so hi, my name is Madeline Leembruggen. I'm so excited to be here. I study what I think of as everyday physics. So I'm going to tell you a little bit about me and how I got into physics, and then I'll tell you about what physics is if you haven't spent much time thinking about physics. And then I have a short video about my specific research, what I did for my PhD dissertation. So a little bit about me. I'm a physicist and a writer and an educator. Some of the things I like are bright colors and all kinds of books. I like trying all kinds of new things to read. I like Legos. You might see a couple in my background. So I like building things when there's instruction manuals. And I also like trying new foods, whether that's cooking new foods or going to new kinds of restaurants. Those are some of the things that I do in my spare time. So, I'm a physicist. How does one become a physicist? Well, when I was in high school, I decided that I wanted to be an astronomer because ever since I was a kid, I liked the stars, but I hadn't really thought about what it would mean to be an astronomer. So that led me to study astrophysics and math when I went to college. But then I decided that I really liked physics. So I kept studying physics at graduate school, and in 2024, I graduated from Harvard with my PhD in physics, and I got to wear this very fancy and kind of silly hat and robe. Now, what I do is I'm a writer mostly. I write for a YouTube channel called SciShow, and this summer I got to film some videos with them, including this one with Hank Green. Maybe you've seen him on their sister channel, Crash Course. And so I write videos for SciShow, and sometimes you'll see me on the channel hosting videos as well. So I love being a writer because I get to learn about something completely new every single week. And that is what I loved most about studying science and doing my PhD was getting to learn something new and then tell people about it. And now I get to do that all the time. And I think it's the coolest thing ever. Every single week, I'm learning about the new physics, about something that I haven't really thought about before. I'm also an educator, so I help design lessons for learning physics and math at school, um, both at the middle school and high school level, and also now I design some stuff for undergraduates as well. So that's my job and what I do with my physics degrees. I want to tell you what physics is. Oops. I want to tell you what physics is so that we can ask some questions about it later on. So, this is how I think of physics, how I define physics. Physics is how matter and energy move through space and time. So, that's kind of a really broad definition. Some other ways to think about it is that physics is the study of basic building blocks of our universe. So, it's a way to study things. And physics is also a model for understanding everything that exists. So I have kind of three different definitions here. It is how matter and energy move, but it is also a study and it is also a model that we create. So it's a way for us to study the stuff around us, and it's a set of tools that humans have created to understand what exists. And we're constantly adding improvements and updates to the tool that we call physics. I think that's pretty cool that physics keeps, like all science, physics keeps building on itself. And the way that we understand things gets better and better all the time. So physics happens at different scales. Let me tell you what I mean by that. Maybe you've heard of quantum physics. That's how we understand molecules and atoms and subatomic particles like electrons and quarks. So this is a very, very small scale for physics to happen on. This is the smallest stuff that we know about in the entire universe. On the entirely other side of things, we can use physics to study cosmology, and that's the study of how galaxies and clusters of galaxies and how the whole entire universe formed. So those are the very biggest things that we can imagine. So we can use physics to study the smallest things that we know about and also the biggest things that we know about. But there's a lot of space in between those two extremes. So what happens in the middle? Well, there's a lot of stuff in the middle. We can use physics to study the cells that make up plants and animals, or the materials like paper and plastic and wood and glass, the materials that we use every day. We can use physics to study that. We can also use physics to create big structures like buildings. And in architecture, physics is a really important aspect to consider because we don't want our buildings falling down. And sometimes we only think of physics as the study of the really small or the really big. When we talk about physics, sometimes all that comes to mind is quantum or cosmology, but there's a lot of really important stuff in between. And that's what I study. I call it the physics of the everyday, and it's all of this stuff that we're surrounded by all the time. And you need different kinds of tools to study everyday physics than you do for quantum or cosmology. So I'm going to next show you a quick video about my specific research and why I found it so interesting. And then we can open up for discussions. I'm going to make sure that my screen share has audio on it. Zoom has moved. Okay, there we go.
I titled my PhD dissertation Buckling, Wrinkling, and Crumpling of Simulated Thin Sheets. It might sound dull, niche, or totally random, but I'm going to convince you it applies to your daily life. I'll start by defining each of these terms. Here's a piece of cardstock, and I'm just applying a force with my hands, causing it to bow out once a certain force is achieved. Buckling is a large change in shape that happens in response to an applied force. Next up, we have wrinkling. This is a piece of soft elastic that's usually used in dental surgeries. When I stretch it and apply a bit of a twist, we get an orderly collection of bends, and their wavelength is much smaller than the dimensions of the sheet. Those are wrinkles. Finally, we have crumpling. Of the three, this might be the most familiar to most of us. By crumpling, I'm specifically referring to this disordered network of folds. These mountains and valleys have formed to dissipate energy in a highly compressed system. In this case, I compressed the paper in my hands. But you could also think about the crumple zone of a car, which is designed to crush and crumple to dissipate energy during a collision. These are really interesting phenomena because the geometry of the deformation gives the material brand new properties. I'm using really physicsy words to describe this, but these are properties we use super intuitively. A floppy piece of pizza can be made rigid by forming a buckle in the center of the crust. And if you try to gift wrap a basketball or a bottle of wine, or in this case, a disc of chocolate, you'll find yourself with wrinkles or pleats to store all that extra paper. And crumpling a sheet can make it both stiffer and more shapeable. A flat piece of paper flops over if you hold it by its edge, but a crumpled sheet can support its own weight easily. This is a common trick that bakers use to line baking tins with parchment paper. While the flat sheet popped right back out and refused to stay in the tray, the crumpled sheet easily takes the shape of the container and maintains that structure. I was really interested in studying buckling, wrinkling, and crumpling so that these properties could be applied to designs of products and new materials. Here's a pen that I was gifted for my birthday. By flipping the switch at the top, the pen compresses slightly, creating this beautiful buckling pattern along the barrel. A sheet of cardstock, or even two stacked on top of each other, are quite bendy, but most cardboard is corrugated, meaning it has a series of wrinkles sandwiched between flat outer layers. Notice that this cardboard is easy to bend parallel to the corrugation pattern, but incredibly sturdy in the perpendicular direction. By harnessing the unique properties of those wrinkles, we've created a material that is much stiffer and far lighter than a solid chunk of paper with the same stiffness would be. And here's a shirt that was a staple in my early aughts wardrobe, the Magic Bubble popcorn shirt. These often come in one size fits all because of how incredibly stretchy and shapeable the material is due to its crumpled texture. The unique effects of geometry produce novel designs, but before we can make full use of these properties, we need to know more about buckling, wrinkling, and crumpling as design components. So I spent my dissertation making computer simulations of thin materials so that we can better understand how to control and apply these deformations. One of the reasons I loved my PhD research is because whenever I felt overwhelmed or unmotivated, I could find new inspiration from the project itself. Here I'm using this shiny ribbon to create all of the deformation modes that I studied using computer simulations. By the way, doesn't my nail polish just perfectly match the ribbon? All sorts of beautiful patterns are created by the simple twist of this ribbon, a reminder that deep, unsolved physics is hiding all around us. I hope I've convinced you that buckling, wrinkling, and crumpling are interesting features in physics. And if you have any questions, just let me know.
So I know that was a pretty physicsy overview of things, but the point I want to get across is that physics is everywhere around us in the stuff that we touch every day. It's not just really small or really big. It isn't just throwing footballs through an air or spinning ice skaters at the ice rink. There's a lot of physics that is in our kitchen and in our homes and in the way that we live our lives every day. So that's all I have, and I'm so excited to answer some questions.
All right, that was really cool. Thank you so much. I am I've been like shipping a lot of stuff this week, and I now appreciate the corrugated cardboard that everything has been like the raw materials have been showing up in so much
Right.
more. I like feel guilty recycling,
Mm.
yeah, instead of
And if
re
you notice, like a lot of things now these days, instead of being shipped with like bubble wrap, are shipped with crumpled paper because
yeah.
they're very good at it's very
Uh-huh.
good at absorbing extra energy and kind of cushioning.
The rest of the day, I'm going to be thinking about this. That was very cool. Okay.
Great.
We've got a lot of questions already. Let's see. Sarah wants to know, a different Sarah from me, how do scientists measure very tiny things like subatomic particles?
Oh, that is a great question. The answer is very carefully. So there's a couple different ways that we can measure really tiny things. If we're talking about atoms, there are certain kinds of microscopes that are able to look at individual atoms. Or if we have a material, if we have like a piece of metal, there are certain kinds of microscopes that can look at the atoms in the metal. We can also use X-rays. X-rays can shine through a material, and then the way that they bounce off of the atoms and the electrons in the material tells us about the structure of the material. If we want to go even smaller, if we want to look at subatomic particles, then we have to create then we have to go to particle colliders. So maybe you've heard of CERN or the Large Hadron Collider over in Geneva, Switzerland. So what they do, we have a couple particle accelerators in the US as well. What they do is they use magnets to speed up protons, usually to like 99.999% the speed of light. So they go really fast and then they smash into each other. And when they do that, they release all of these other little things that kind of break into all of the components that they're made of. So protons are made of quarks, and there's some other stuff that goes on. And then we can look at what comes out of those collisions, and it tells us something about all of the particles, the subatomic particles that make up the protons, and make up atoms more generally. So that's an indirect way of looking at subatomic particles. But for now, it's the best that we can do. Unfortunately, we don't have microscopes that can look at subatomic particles yet. So we've got to break protons apart in order to see what's inside them.
Cool. Thank you. Our next question comes from Bluey Williams' class. How do Newton's laws of physics fit into your study?
Ooh, I love that question. So I made, because it's about my research, so of course I love it.
Yeah.
I made computer simulations of these very thin materials, things like paper or tin foil. And the way that we made those simulations is we took a sheet and we broke it up into tiny little triangles. And every single triangle, every single vertex of the triangle was connected to each other by little tiny springs in the simulation. This is how we modeled it. So those springs follow what's called Hooke's law, and Hooke's law tells you what the force is. So the force is proportional to how much the spring is compressed. Now, whenever we have forces, then it's starting to look like a good time to use Newton's laws of motion.
Mhm.
So in our simulation, what we said is here are all the forces that are going on in these triangles that make up our simulation. And when we add up all those forces, we know that the sum of the forces is going to be equal to the mass times the acceleration. And then the acceleration tells us how the vertices, the vertexes of the triangles are going to move. So you briefly saw those like clips of the simulations that I made, and they're these sheets that are moving and compressing. And all of that comes down in the end to Newton's laws. In my simulation, it said F equals ma, and that A, because of all those forces that we add, the A tells us how each of the vertices moves, and then overall, how the entire sheet moves.
Awesome. Thank you. Our next question is really interesting. Why do some things stay crumpled and others don't?
Ooh, so what causes a crumple at the microscopic level is so in paper, the paper fibers that make up the sheet of paper, they get kind of ripped a little and rearranged. That some of their bonds break and then they stick back to each other in a new orientation.
Mhm.
So if we create a fold, then that is what's called a plastic fold. Plastic versus elastic. Elastic is something that springs back to its original shape. Plastic meaning that it keeps some kind of memory of the way that it was folded or deformed before. So when we create a crease, what we've done is change the microscopic structure of the material and it holds some of that damage. It kind of has like a memory of what happened to it. So in paper, that's the paper fibers realigning and rebonding. In metal, in like tin foil, something similar happens. In a metal, you have all of the atoms kind of lined up in regular rows. Like paper fibers are kind of these long things that tangle up together. But in metals, we have all of these atoms that sit right next to each other. And um, they can slide with respect to each other and they can shift position. And so, in the same way that the paper fibers kind of retangle in a new way, the metal atoms can rebond in a new orientation. So some materials are capable of holding this kind of plastic damage. They have a chance to keep the memory of what's been the deformations that they've gone through. Other kinds of materials don't have that. So if you have a really stretchy plastic, those are very good at like the one that I showed where it went like this and then it got the wrinkles. Those have really long molecules called polymers that kind of stretch and they're good, but they're good at hanging on to each other as they stretch. So then when you let go of it, they just spring back to their original position. So they never did that rearrangement that holds the damage. So that's why fabric or a really soft piece of plastic, they won't stay crumpled. And that's because their fibers are really good at keeping the same position even after we let go of it.
Cool. Awesome. Really good answer. Thank you. Our next question is from an anonymous attendee. What classes did you take in high school to help you on your path to becoming a scientist?
Yeah, that's a great question. I took physics in high school because I wanted to see if I was good at it and if I liked it enough to study it in college. So I took physics and I took chemistry in high school. I pretty purposefully chose my math classes. So I made sure that my high school offered calculus, which was really great. So I made sure that I arranged my math schedule so that I would be able to take calculus at the same time that I took physics. Calculus is really important for studying physics. So the primary classes that I took in high school that helped me get there were calculus, physics, and chemistry. And before you take calculus, you also take usually a pre-calculus, and geometry is really important too. Being able to understand things geometrically is a big part of the way that we think as scientists and physicists.
Awesome, thanks. We have a number of people kind of asking around the same question, including Addie from Garden Spot. I think elementary. There might be a Garden Spot middle as well. How old were you when you first decided that you might want to become a physicist? And what originally got you interested in physics?
I for a long time didn't have any idea what physics was. When I was the first time I remember being really interested in stars was actually in kindergarten. I had a book about stars that I would read over and over and over again. And when I would go out, when it was still like a little dark out and I could see the stars, I just thought they were really cool. And so I think when I was in elementary school, my parents, bought me a couple books about the universe and the solar system. But I kind of forgot about that interest for a very long time. Maybe some of the people here have the same problem where they're just kind of interested in everything.
Mhm.
When I was in high school, that's how I felt. I was really interested in music. I was really interested in books and literature. I was really interested in teaching and working with students directly. So I had a lot of different interests, but I kind of sat back and I said, okay. I think I'm gonna go to college and I can do anything I want in college. And then I remembered that I really liked the stars. And I said, well, someone has to be an astronomer, so why shouldn't it be me? So I went to Google and I Googled how to become an astronomer. And Google said that you needed to study physics first. So that's when I decided that I was going to take calculus and I was going to take physics, and I was going to see if I liked them, and if I liked it, then I was going to apply for that in college. And I would say that I didn't realize I wanted to be a physicist until maybe my junior or senior year of college. In high school, I decided I was going to study physics, but when I got there, I didn't like astronomy I didn't like the reality of astronomy as much as I thought I would. So, but I liked the reality of physics. And for a long time, also in college, I didn't know that being a physicist was like a career. I didn't know that that was something that you could do. I especially also didn't know that that was something that women did. I didn't know that it was something that people who are not white did. And so I'm a woman and I'm Filipino, and I had never considered for myself that that was a career path I could have. But I had really great professors who told me that it was possible and it was something that I would probably be pretty good at. So around my junior year of college is when I decided, okay, I'm going to go to graduate school. I'm going to be a physicist. I'm going to do physics research and see where that takes me.
That's awesome. Thanks. All right, we've had a bunch of different classes from all over the place asking about that machine that you've got going on. I know you sort of gave me once
Yeah.
before we started recording, but could you tell us what that is, how it works, and yeah,
Yes.
what it's all about?
So this is a double pendulum. So maybe you've learned about pendula, or you've seen them before. Like a big grandfather clock has this big pendulum that swings back and forth. So what's the reason why pendula are used in clocks is because they swing back and forth in a very regular way. We can exactly predict where it's always going to be. But if you add a second piece to a pendulum, it becomes what's called chaotic. and you can no longer predict how it's going to spin or where it's going to go. That's why you see it kind of tipping and turning and tumbling, and then every once in a while it'll switch directions, like right now, switch to the other way. And it's not possible for us to predict when it will switch or where it will go next. And this, it looks like a perpetual motion machine, but it's not. I haven't broken physics. There's a little magnet in the bottom of the long bar, and then there's a battery in the base. And so every time this long bar swings around, it gets kicked by an electromagnet that's powered by a battery. So the magnet in the base gives it some more energy to keep pushing it around and around and around, and continue its chaotic path as a double pendulum.
Okay, I have like a real baby simple question here. So when you play with magnets, you can like get them to go away from each other. All right.
Yes.
What is the deal with electromagnets? Like, why
Mhm.
would you electrify some? Like, if you had just a non-electric magnet at the
Yes.
bottom, why wouldn't is that sometimes, if it was a strong enough not electromagnet, enough to oomph it over? Like, what's that all about?
So the electromagnet allows it to respond to the direction of so the magnet that's in the long bit.
Uh-huh.
Um, when you add electricity and magnets in a circuit together,
Uh-huh.
they are able to respond to the direction that a magnet is going. So if there's no battery in there, then it just does like a repulsive, it just kind of sits there and repels the magnet in the long bit from the magnet in the base. But with the battery in there, then it makes a complete circuit that then can give it a kick that's opposite the direction it swings. So we'd have to like get pretty deep into the details to go further than that. But electricity and magnetism are all part of the same force, and so the way that um, when you add electricity, then it unlocks new ways that you can use magnets, which is why we need the battery in there.
Very cool. Thank you for that. Okay. Okay. From Garden Spot again. Do you have to travel for your job?
I do travel sometimes. So for my job as a writer, the SciShow studio is located in Montana. So when I go film videos with them, I get to go to Montana. Sometimes I also go to conferences. This year, I helped with a couple film festivals. I'm also really interested in creating like documentaries and films about science. So for that this year, I got to go to New York City, and I got to go to Wyoming, and those were really fun. Physicists in general actually travel a lot for work. If you do, I mean, that's the way that I travel as now a science writer, a physics writer. But when I was still an academic, when I was still at universities, um, I traveled a lot for conferences. So experimental physicists, sometimes they travel to go see their experiment. So one of my friends, she studies a subatomic particle called neutrinos.
Mhm.
Well, an elementary particle called neutrinos. And so sometimes she goes to Spain because there's an experiment there. Sometimes she goes to Japan to see the experiments over there. So a lot of experimental physicists travel to do experiments. And then even theoretical physicists get to travel. They go to conferences so that they can talk together and work on new ideas. Sometimes we have just meetups in really pretty locations so that we can be inspired by nature and talk to each other and learn from each other. So if you like to travel, being a scientist is actually a pretty good career for that.
Yeah, I just got back from Japan for a squid conference, which was pretty.
Oh,
We were in
so fun.
Okinawa. Yeah, it was very fun. All right, we got a question from Izzy from Mr. Alfred's sixth grade in Jamestown, Rhode Island. How small does something have to be considered quantum?
Ooh, okay. This is kind of a tricky question. So the there are some systems that when you make them really, really cold, really, really, really cold, then it will behave in a quantum way, even though it's kind of big. So I would say at room temperature, what is considered quantum is about the size of an atom, maybe even smaller. We would consider a single atom kind of quantum, but the way that the atoms interact with each other, like in the room temperature air, you don't necessarily need a quantum mindset for the way that the nitrogen and the oxygen atoms in the air interact with each other. So, but if you're smaller than the atom, the scale of about an angstrom, that's 10 to the minus 10 meters. So that's pretty small. That's at kind of room temperature where we would consider things quantum. But certain experiments take really big molecules and they can make it cold enough so that you can get quantum effects even on like the centimeter scale.
Hmm.
So that's 10 to the minus 2 meters. So depending on your temperature, you could either be at 10 to the minus 10 meters or 10 to the minus 2. Um, but cold is the other side. There's cold and then there's size. So if you make something really cold, then you can get it to start acting quantum even without going really small. So that's one of the ways that this field of like quantum computing and we talk a lot about quantum information too. The way that we study quantum systems is by making them really cold so that we can make them bigger and see them better.
Cool. Thank you. We got a very topical question from Holly Wilder Stutz's class related to your interest in stars. Can you tell us anything about the astrophysics involved in the current solar flares and unusual aurora visibility?
Ooh, so I don't know a ton of specifics about this, but I'll tell you what I do know. So the sun goes through cycles where it has various amounts of solar flares. And a solar flare is a section of plasma from the sun that kind of breaks off. We still don't fully know why all of these happen. It has something to do with the sun's magnetic field, but pieces of plasma will snap off, and then the particles from that plasma drift into the solar system. One of my favorite things about our planet is that we have a big invisible force field that protects us from the rest of the universe. So Earth has a magnetic field that surrounds it, and it protects us from all of these like really fast, high energy particles that are zipping through the universe. So when this plasma comes from the sun, like it's called a solar wind sometimes, when it comes from the sun, what we see when we see the aurora is literally um, our force field protecting us from those particles. So the particles come from the sun and they interact with our magnetic field, and they emit um, they glow with these beautiful colors as they get kind of deflected and pushed away from entering our atmosphere by our magnetic field. So that's my understanding. The reason why we're seeing a lot of it right now is because the sun goes through cycles. Something about its magnetic field, it seems to have this 11-year cycle. So 11 years ago, we would have been seeing a similar kind of increase in aurora, but especially this past time, the the coronal ejections have been even bigger than I think they were 11 years ago. So we've gotten a lot of really pretty shows the past
Yeah,
couple
for
of years.
sure. Every time Philadelphia's been overcast, so I've been like,
No, I still haven't seen them yet. I'm so jealous of everyone who's been seeing it
every
because I
time
haven't had a
they
chance
like go
yet.
across social media, I'm like, wow, it's so pretty.
Yeah.
All right, we got a question from a group of students in Costa Rica. How has the need and use for physics evolved over time?
Ooh, how far back should we go? Um, so I would say that everyday physics has always been super relevant.
Yeah.
So, one of the most important inventions in all of the history of humans is inventing clothes, inventing fabric, because this allowed us to do a lot of really interesting things and do things more efficiently and, stay warm and keep our skin safe. So maybe we don't think of clothes and fabric as physics, but the way that that yarn is woven into a material, that's all physics right there. You could even say maybe cooking is more like chemistry, but there's elements of physics and chemistry in cooking. So I would say everyday physics like that, things like making glue, that's also chemistry and physics, and glue was a really important invention. So that has always been really important for the way that we live our lives. As we've unlocked new types of physics, as we've learned more about the world, we discovered quantum mechanics about 100 years ago. It was actually in 1925 that we kind of officially decided on quantum mechanics. And since then, we've been able to use that technology to make computers and cell phones and better electrical circuits. Quantum mechanics changed the way that we understand electricity and magnetism. And of course, when we discovered electricity and magnetism, that also revolutionized the way that we lived in the world. So I would say that every bit of knowledge that we've had about physics has always been super important. And as we unlock new kinds of physics, it just also continues to be important in those ways. Um, and even the stuff that we've known about for a really long time, even this like everyday physics, we're still thinking up new ways to do things. So in the kind of research that I did, I had friends who are now working on making new kinds of clothing, new types of materials out of uh, out of knitting and out of fabric with new kinds of functions. So that's something that we've known about for thousands of years, but there's still ways that it's relevant and innovative and evolving.
Super cool. Thanks. Right. Mrs. Harrington's class wants to know, was learning physics hard at the beginning?
Definitely. Yes, definitely. So one of the things that I love about physics is that it's so related to the way that we live our lives. If
Mhm.
you look at the world around you and pay attention, there's a lot of things that we intuitively know about physics. And so sometimes when you learn physics, you're like, okay, well, it was kind of hard to understand how that equation describes this thing that I know, but this thing that I know from life like makes a lot of sense. So, okay, now I have an equation for it. Those were kind of the easy pieces. But occasionally in physics, there's a result that is true, but just feels so different from the way that we live our lives.
Mhm.
So there's a lot of counterintuitive results, and those were always hard for me to learn. And I would say that when I started studying electricity and magnetism, that's when it got really hard for me,
Mhm.
because I hadn't spent a lot of time playing with electronics. Electricity isn't something that we normally see. You know, we turn our light on and we expect that it will work. But because that was a completely different way of thinking, and because it was a kind of thing that I didn't have a lot of intuition for, because I hadn't experimented with it, I didn't live with it very much. Electricity and magnetism was really hard for me. Um, and things kept getting harder. Like quantum mechanics is so weird because it's so small that again, we don't see it, we don't touch it every day. Well, we we do live in it, but not in the way where it sticks in our brain. So I would say every time I learned something new in physics, it was difficult. Um, but it was worth it to keep going and to understand things in new ways and to stretch my brain and to stretch the way that I saw the world. Every time I learned something new, it was difficult in a really satisfying way. Like when you do a sport over and over, or when you practice a musical instrument, um, every step that you take and every time you keep trying, you add a new layer of understanding and skill. And I think that's how physics and math both were for me.
Very cool. Thank you. Right. Our next question is from Ms. Patakis's class. Um, how do you use physics to study cells?
Yes, so this is kind of a newer aspect of physics. We call it biophysics. And one of the ways that people are using it is to try to understand, in biology, we say, okay, here's how things happen. And that's kind of giving a name to the pattern of things. And in biology, things are really, really complicated. So often what we do is we just say, that is the way that it is. There's a cycle that things follow. And sometimes you can follow the specific chemicals or proteins throughout the cell and track what they're doing. And so that might be like biochemistry or might be another way to look at things. And so biophysics is applying principles of physics as well. So what does the pressure in a cell tell the cell and how it responds, how we can look at the way that cells move with respect to each other. So the way that a cell swims or um, the way that they grow next to each other, how that informs their shape. So we can look both at the structure of the cell itself, the physics of that structure, or we can look at the ways that they interact with each other and push on each other. That's also physics. So this is still kind of a new and developing field of biophysics. And there's a lot of really exciting ideas about how we can continue to apply principles of physics to things like cells and living systems to understand things in a different way. Like I said, physics is a model. It's a way to think about something. And so in biophysics, that's a lot of what we do is we make models and we say, is this useful? Is it actually describing the biology that we see?
Awesome. Our next question comes from B9ers, third grade. How can physics help with the environment? Can we make fuel from garbage using physics or solve other environmental problems?
Yes, absolutely. Physics can help with environmental problems. So this has a little bit of intersection with, I think, the field of chemistry, but physics and chemistry, in a lot of ways, go hand in hand. So physics is the study of energy. It's the study of matter and energy, which are related to each other. And energy is a big part of what we need to understand better to solve a lot of the issues that we're facing with the environment. So physics can help us understand more efficient ways to generate energy. It can help us understand ways to conserve energy, um, and yeah, create new kinds of fuel or reduce friction and reduce the amount of energy that we're losing in the way that we in the machines that we have that currently generate electricity.
Hmm.
So there's a lot of ways that we can use physics principles to do this. There's also elements of we can use physics to understand things like how to better insulate a building. Thermodynamics is a kind of physics. And so when we study heat transfer, it's not just about creating energy, it's also about making sure that our homes are more efficient or designing buildings in a way that they reflect a lot of heat and like keep the inside cool. So those are aspects of design that we can also incorporate physics to create more efficient kinds of buildings.
Excellent. Thanks. Okay, so we are coming up on the end of our time here, and we always ask all of our scientists the same two questions at the end. The first question is, if you had everyone's attention in the whole world and you could tell them one thing about your area of expertise, what would it be?
Oh, that's such a big question.
The next one's even worse. So,
Okay. So the first thing that comes to mind is like, what do I want people to know about physics and my kind of physics particularly? I want people to know that physics isn't scary. It's something that we live in, it's something that we experience all the time. We all have a lot of intuition for physics and the way that the world around us works. And I think physics gets a bad reputation. It can be really intimidating and scary, but it's something that belongs to all of us because we're all living it all the time. And I think learning any amount of physics is going to give you a new way to think about the world and understand the world. I love physics because it helps me appreciate the world. And so I'll take a walk around my neighborhood. And because I know physics, I can be like, oh, it's so cool that the leaves are changing. It's so cool that the sky is really blue today. It's so cool that we built these beautiful houses on this street. So, yeah, I want people to know that physics isn't scary.
awesome.
It
Very, very
can be, but it doesn't
interesting.
have to
Yeah.
be.
Yeah. I remember when I was young, I was scared of physics for sure. But yeah, I'm less scared now. Knowing that it helps me use my microscopes to see my little squid cells,
Absolutely.
it definitely, when it helps you out, becomes less scary for sure. Okay, the next question. You still have everybody's attention in the world, and you can
Okay.
tell them another thing, but it can be about absolutely anything, and it can be as like significant and big picture or like silly and like your special interest, whatever you'd like it to be.
Mhm.
What do you tell everybody?
Um, So the other thing that I'm really big on is that asking silly questions is important. I think it's really important to to ask questions that just seem so outrageous. Some of my favorite questions I've ever asked is, things like, is a soup dumpling, is that a sandwich or a soup? Or like, what is a soup dumpling?
Uh-huh.
Or, how, like, what would happen if the moon just all of a sudden disappeared? What would happen to the Earth? So
Uh-huh.
I think asking silly questions, no matter what kind of form they come in, and having conversations with people about those silly questions, it can teach you something new about the world, but more importantly, teaches you something new about the way that you see the world and the
Mm.
way that you think. And so if I would if I would encourage people to do anything with their time, I would say you should be asking more silly questions and tracking down the answers because they'll probably surprise you with how interesting they are.
Excellent answer. That silly questions are so critical. I'm all for it. Amazing. Okay. Well, thank you so much for taking the last 45 minutes to talk with us and share all of your information with us. This was really cool. Everybody at home, or at school, more likely. I just thank you all for coming. Again, if you we have always like so many more questions than we can possibly get. We have 78 unanswered questions. So if you and your class want to talk to a physicist, you can always request a physicist just for your group, or a chemist or a marine biologist, whatever category you want. We're a little tight on archaeologists right now because of a Lego competition, but otherwise we can get you whatever you need. So you can go ahead and sign up, have the teacher or club leader sign up at skypeascientist.com. Other housekeepy things, we have these like calendars that they're all about different animals, like cuttlefish and bats and crows and anglerfish. It's not all ocean stuff. We got, urban wildlife and salamanders and newts and all sorts of stuff. These help us keep Skype a Scientist running. So if you like animals, and you need some art in your classroom, and maybe also keeping track of what day it is, calendars. They're cute and fun, and you can get them at squidfacts.net because you catch squid with a net. So squidfacts.net. If you'd like to help keep our program running and allow us to, hire ASL interpreters and do programming like this. So you can do that, squidfacts.net. Get a free scientist for your group. That is all of the things I have to tell you today. We are going to be back here talking about snails and how climate change is affecting ocean snails next month, with Andy Lee. It's going to be a delight. So we hope to see you there. You can sign up for that at skypeascientist.com under the live streams tab. Madelyn, one more time, thank you so much for being here
I
with us.
had so much fun. This was great. Thank you so much for having me.
Awesome. Thank you. We'll see you later. Thank you, Jessica, as well. Bye.